Yep.
Hat im Chat geschrieben, dass wir
Okay, I hope people online can hear me as well. The second notebook, which is much more experimental, so I'm really curious to see if it works out. We'll see in a second. We're going to use MatchMS, but we're mostly going to focus on a tool that was built on top of MatchMS, and that is MS2DeepScore. And this is a tool where we try to approach spectral similarities a bit differently. So the motivation for this is that, as you might be aware, that we have scores that are commonly used, like cosine score or modified cosine scores, and many variants of those, and they can do quite some things. So with the cosine score, that's really intended for exact matches of the spectra. So if you really have a spectrum of the same compound in a similar way measured, you can find this with a cosine score, hopefully. And then there's concepts like the modified cosine score, which, if you look at how they are built, they make certain assumptions about how molecules change and how this affects their peak patterns or their fragment patterns. And so they are able to find compounds with individual changes. So you have certain groups that have been removed, and then you can still find those changes back in the spectra by a shift of masses or by mass shift. And these scores work pretty well for what they are meant to be used for, but they have some limitations depending on what your use case is. So one thing that will not really work is they are not able to find similarities between, or meaningful similarities between, two spectra of compounds that underwent multiple changes. So let's say you have a more complex molecule and you have changes in several different groups, then neither the cosine score nor the modified cosine scores are really meant to be used to find the chemical similarity that might still be present between these two compounds. So usually they will just give you some arbitrary score or a low score. So they're not really intended, they're not really meant to be used for these cases. So let's say, like, for further away, but still chemically related compounds, those two methods might not be ideal. And let's say the second thing is the same here. That's it's not an ideal proxy, let's say, for chemical similarity, because what you're asking for is kind of you look for similar fragmenting patterns, and that might also change depending on your measurement settings, but it might also indeed overlook very high chemical overlaps, or especially, let's say, slightly larger molecules, but with individual changes at multiple places. And so we realized that we were actually after something different in the project, management project. And that was more, we were looking for spectra that belonged to compounds with high chemical overlap. So the core idea is that we aim to see if we can learn benchmarks from available annotated data. And so this means we take spectra from across the full range of chemical similarities, and chemical similarities is a whole field on its own, so I'm not going into details here. What is chemical similarity, how do you measure it, and so on. So there's a whole debate that you could fill with this. We are simply using a NTMSS score based on fingerprints as they were introduced in the series presentation, right? So presence, absence fingerprints of certain chemical structures, and NTMSS scores, and so this allows us to give a number to the chemical similarity to two compounds, a number between 0 to 1. And the idea is that we want to have a tool that tries to predict these scores for spectra. So it doesn't know the compounds, but it only sees the spectra and tries to predict how similar the relating or the underlying compounds are. But the way we do this is the following. So we have the fragmentation patterns, and because this is, I mean, with a high precision, this is kind of not handleable for most machine learning tools. So what we do is we do a binning step where we say that, okay, this is a bit crude, right? So we lose information, but we have to do this, and we kind of put them into let's say 0.1 Dalton wide bin, and say, okay, this is you get a vector from this, and it says, okay, at the place where we have these peaks, and this is the pointer here, so you will get some kind of value in each array of numbers, and this value will be the intensity of such a peak. And of course, that means kind of if we have two peaks which are really close, they may end up in the same bin. That will be kind of accepted. But this is what we do. So we reduce this fragmentation pattern to about a line of 10,000 numbers. And this line of 10,000 numbers is then feed into a neural network. And this neural network is trying to compress the information. We don't go into the details of the neural network here, but what the neural network is really good at is dealing at a lot of data and trying to find patterns in complex data from large data sets. And so what we try is kind of to bring this down from 10,000 numbers to something like 2, 3, 4, 500 numbers. What do we do with this? I mean, this is not very useful yet, but in the end, what we do with this is this is what we call our base network. And we use it in a prediction, we use it 2 times. We use 2 times the same network, and we use it the following way. So we have spectrum 1 and we have spectrum 2. And we give this to the same network twice, like the same network, spectrum 1 and spectrum 2. And then in the end, the outcome in compression, we will compare with a similarity measure and get a score. This is of course not useful because how can it learn anything from this? It can only learn anything from this if we tell it what it should ideally get out of this. So this we do in the following way. So we train it with spectra where we have annotations. So in the scheme that we saw yesterday, it's mostly, I would say, level 2 annotations. So what we get when we download GPS data, there are faulty annotations for sure. It's not clear reference number like this or so, but it's we assume that these are the true labels here for now. And so we know that for these spectra, we have smiles and inches. And since we have smiles or inches, we can also compute the true score, right? Or the true, what we call the true score here in our conception. And this means that we have 2 spectra. We know ideally what the Tanimoto score between these 2 spectra is. And now we ask the network, please predict the score for them. And this is how it learns. And whoever is not into machine learning, be skeptical about anything that's with the word intelligence or learning in there. It doesn't have to do anything with what humans learn, but it's kind of optimizing statistical functions, or you could say it's optimizing functions towards seeing a lot of data and trying to be as close as possible to the original score, if it manages to find patterns. And this we do with many millions of spectral pairs that we pick so that we have all Tanimoto score ranges. And then we hope that it is able to predict chemical similarities by only looking at the spectra. So the network, the neural network, will never see what you see on top. This is only for us, for training, but the network will only see the fragments. What you see in red here is kind of that to give it a bit more variation, we do some modifications sometimes to the spectra randomly. So we slightly do alterations to shifts, to peak intensities, and so to account for whatever can happen during measurements. And this is what it's doing. It's the whole network. We train it. This is what we're going to use now in this session. So we're not going to train a model. This takes too long. We are going to use a model that was trained on about 25,000 compounds and about more than 200,000 spectra. Just to give you an idea, so we're not ChatGPT level deep learning here. This is really small scale things still for deep learning people, and you can run it. You could train your own network on your regular computer in a day or a night, but clearly not in Google Colab for a live session. So what we want to do, use this for is to predict Tanimoto scores. And of course, these are predictions. That's always good to remind yourself these are predictions, and there's a lot of false predictions in there because it's very difficult to predict from fragmentation patterns the Tanimoto score. But it can be used. We have shown in the paper that it's fairly good at identifying Tanimoto scores to a decent accuracy of, say, 0.1, 0.2. And you can use it for something like molecular networking. Also, I have to warn you, these networks will look very different from the networks that you get when you use 45% score. But we can also do something different, and that's what I try to do now in this session, is to get chemically informed embeddings. And embeddings means that we get these vectors out. So we get a row of abstract numbers, and hopefully they somehow represent, although we derived them from a spectrum, I hope that they somehow represent chemistry that's decoded somewhere in there. This we're going to see in the notebook, I hope. So I switch back to the notebook. Yes. So okay, I switched down to try something because we got some issues with version. So ideally, you opened the notebook before the break and you installed. You ran this. So I pip install MS2DeepScore. This takes longer than the last time. It still should run in a minute or two, but it's installing these deep learning frameworks, and they are fairly big libraries. So that's why we do this in this notebook version, also because they are known to cause trouble in your local computers, but you should be able to get it to work eventually. If you're there, if you install this, then this code should execute fine. And we will go quickly through these code cells because they are exactly what we did before in the other methods. They should be exactly the same. So the first steps are completely identical, so we can go very quickly through them. The only change is that we also imported pieces from MS2DeepScore. The other code cells you can ignore for now, you can only afford to ignore them if they work, but then you can ignore them. It's remount the drive again. Drive. And if we mount the drive, then we have access to the file that we used before. So this all should look familiar. It means kind of we import the spectra, we process the spectra. Oh, sorry, I think there's still the I have the wrong. I'm in the right notebook here. I hope I am. Otherwise, I'm destroyed. Just check it in the right drive. So pretty quickly, I had through these notebooks and just execute them as long as there's no question there. I'll just see if I'm in the right one. Sorry, for me, it's a different folder. You don't have to change it. It should be, for you, it should be working as it is, or you change the path. So once we have the spectra imported, okay, you can see if it's the same number, just to check, it should be the same number that you used to have before. And we can skip the explanation part because this is exactly what we did before. It's just that we here use a new notebook to not confuse things. So we process the spectra because we here now really depend on the activity, and we really want to remove spectra which have 0 or 1 or 2 peaks, or 3 in this case. Where you set the limit is not so critical, but it means kind of MS2Deepscore, as we've seen before, it's kind of doing this bidding. So it only looks at the fragments, and if it gets the 0 fragments, it can do nothing. With 1 fragment, it can be very little typically. So the more fragments in the spectra, roughly you can say the more patterns it can detect. If it's optimized, of course. So what I switch now to is this MS2Deepscore part. And as I said, this is a model that is provided in the Google Drive. The file name, and this is a model that is pre-trained, so we can load it. And this will be now a bit difficult for people that have not mounted their drives because this model is not huge for deep learning standards, but it's still like 150 megabytes. If you want to upload it, it might take some time. But if you have mounted it to your Google Drive, then you should simply be able to execute this code cell hopefully. And actually, really quickly, what we do here is we say what the model is, and we load the model. And then we have our deep learning model imported into MS2Query. And so the way it's programmed is kind of this thing that we just do here can be used as a similarity score within MS. Let's see if this works for you. Is there somebody where this doesn't work if you have mounted it? So you can make it. Are you looking for the model itself, or is the model itself? Oh, yeah, sure. Yeah, then you can but it should be on the shared drive. But so even if it doesn't work for you, so if you have no files, or the file upload is slow, in the Google Drive, there's also a solution of this notebook provided. So I think it should be fairly simple afterwards to also go back and check this again. Let's say you have this imported, then you can do something, and that is a bit slower operation. You could use scores. I'm skipping this step on purpose now because that is the slow part. We can do this live, but in view of time, I like to jump ahead a bit on a second use case. I mean, we could do something like this. We could compute the scores. This would actually, what this would do is it would compute the scores between the 3,802 spectra, all versus all, and it would predict a Tanimoto score for every possible pair of spectra. And then you would get a huge array that says, okay, between spectrum 100 and 100, spectrum 101, I predict a Tanimoto score of 0.7 or something like this. And you can create anything you like from this. You could build a molecular network, for example. So if you run, I mean, you can run it later in the free coding session or at home, and you can see if you do this, the code is provided in here. You can eventually, with MS, you can create a network, a graph. So you would have to fill in what's the score cutoff, the number of links you want to add, and you can create a graph in our file. So with this, you could export this, and this is the format you learned to know yesterday. You can immediately import into Cytoscape. So you could create a network from predicted Tanimoto scores. Indeed, what I'd like to focus on now in view of time is more the second part, what we can do, because this is a bit less common application, I think. And this is, we've trained this network on predicting Tanimoto scores, but it also internally stores this compressed version of the fragmentation pattern, right? So it gets these 10,000 numbers in the beginning, those are the zero, but it then compresses it to a few hundred numbers. And this is what we in data science or in machine learning call an embedding. So it's something that is in an abstract vector space, something that is kind of, I don't know, you cannot make sense of the numbers don't make sense to you, but it hopefully will find a position such that two spectra that are very similar should be in the same corner of this space. And this has some quite useful properties if it works. So you should install this one here. I think this just in the break, but this is typical. So we need another package that's called UMap, so UMap Learn. Who has worked with and not only this, but who has worked with UMap before? Who knows either UMap or TSNE as what they are doing? I think not the algorithm details, but what they are used for. So then I will briefly mention what they do. So there's a number of tools that are meant for, data science we would call dimensionality reduction. We have seen other tools like this. A fairly common one is PCA. So the aim of these tools is if you have something that has a lot of numbers, like a vector with 200 or 500 numbers, you cannot visualize it at all. So what people often do is kind of we try to compress it, accepting that we lose information, but compress it to 2 or 3 different entities, because then you can make a plot where every data point has a position that you can plot. And you can use PCA for it. It's a linear technique. It's not great for all the things, but for some it works really well. And then there's recently, not so recently anymore, but in the last 10 years, there's at least 2 tools that are fairly standard now. One is TSNE and one is UMap. And I'm not going into details about these tools here, but they do a bit better job typically in compressing complex data. At least visually, it's usually what people prefer. And so we're going to do this with our vectors. So for this, we have to install UMap, which is also provided in Python, luckily. And then the costly step is this one. This will cost you a bit of time, because what we do here is we will convert all spectra into bit spectra. This is very quick to see, but then what this is doing is kind of feeding every spectrum into this deep learning network. And what we get out of this is, I can show the slide again maybe. I will just go back to slide 4. So what we actually do is kind of we feed it all the spectra in our data set now, every one of them, and then we get some numbers out. And this is the numbers, so the numbers at this point, which we now will store. And this will take some time. So we can Wait for this to finish. It's not super bad, but it will take a few minutes. In the meantime, I can take questions if there are any questions on the scene so far. And we can also look at some trouble if there's trouble running this scene. Yes. Oh, yeah, sure. That's all good. That'll be good. Yeah, everyone's trying his best. Is there any questions on what we're actually doing here, maybe, or what we? Yes. Yeah. So. Yes and no. So usually, if you want to use these tools like PCA or TSME or UMAP, you need to consider pre-processing. So these tools assume that you have vectors that are having numbers of equal range. Otherwise, they won't work nice. They will not fail, but they will give you weird results. But here, when we get these vectors, they are already good to go. So once we get these vectors, we can immediately put them into PCA or TSME or UMAP. We don't have to worry about the data processing anymore. The only thing we have to worry about the data processing is what do you give as an input to MS2DeepScore. This is why I, for example, removed the spectra with only 1 or 2 peaks. You will not complain, it will work for them too, but I don't trust the results very much. But otherwise, other than that, you don't have to do a lot of pre-processing. And also it turns out because of this deep learning network, because the intensities are in there too, even if you have noise peaks or if you remove them, it changes hardly anything. So it's more about, okay, you need to have, of course, the better the spectrum quality, the more fragments you have, the more information you can potentially get out of this. But there's maybe now that we have time, so where this I should also mention another thing. There is, of course, we trained it with GNPS, this network that we're using here. So what it can do well is, I assume at least, is it can predict well chemical similarities between compounds that are often found in GNPS, right? But there's, I think the more exotic the compounds get, the more rare they are or the more different they are to the standard of what you see in GNPS, the less I would trust these predictions. But I guess that's a problem with all data-driven tools, that you rely on the data that you can train on. So the next step we're going to do once this is finished is kind of we give this to UMAP later on. So what this will give us is we can also look at what it actually gives us. I think it should be this. So we also check what it actually gives us. Vectors. So what this produces, you will see in a bit, is we get a vector for every spectrum. So we get 3,800 lines of numbers, which represents somehow, hopefully, what's in the spectrum a bit. And of course, as I said, so they will be, depending on the model that we use, in our case, they will be compressed to 500 numbers per spectrum, which is far too much. And we are going to compress this further with UMAP. If it works. And for this, the UMAP will also take some time, of course. One thing that is not filled in the notebook yet is, and you can think about it, is kind of you have a couple of parameters in UMAP. So UMAP, you have a random state. This is only because there are random initialization steps and random processing steps. And they're only reproducible if you set a random state. So you started with a random number. And then there are two main parameters, and those are important. The number of neighbors you aim for and the minimum distance between dots. Those two are things that you can tweak, and there's no right or wrong here. So it's not, as we now come to a big problem in this field, there's hardly a way to judge how good your data dimensionality reduction works. So it's up to you visually to inspect how it works. I would recommend for you to say neighbors to the higher number, like 20 for a start, and the distance, I think anything like 0.2, 0.25, 0.3, 0.4 is fine. So I set it to 20. The higher, you can look it up, I think there's a link in there. The higher this value is, the more you look into global patterns, and the lower it is, the more you look into local patterns. Okay, so this is done, at least for me. And if I look at what I got, is I got an array, a number array with 3,800 rows, and each of them is for 1 second, and they are 500 numbers long. So what we get, just to let you know what this vector looks like, or doesn't look like, is we can do MS2DS vectors. I will take the first spectrum, and then you'll see something weird. This is how it looks like. I can tell you straight away that I never look at these numbers in practice, of course, because I mean, I'm checking if they make sense, if there are numbers in there, is it just something weird. But some are surprisingly high here, for example, but this is a vector, so it has a lot of zeros in this case. But I cannot influence this so much, because this is what the network learned to compress its spectrum. And you can immediately see that this is nothing that helps you any further. So let's only count the first 20. These numbers are totally weird for you. So this is to say that with this vector alone, you cannot do much. But if it's trained well on a good set of data, this should contain or should encode for quite some important feature pieces of this network, of the spectrum. And so you can use it for multiple things. You can use it to train other networks, but what we are going to use it here for is to compress it further. And I'm not curious if this works because we had some trouble before. This piece of code, so I think in your notebook, it's only import UMAP, which worked yesterday evening for me. It didn't work this morning. So I changed it to this one. Depends on what, if you get an error that says something about number or NPython, and change it to this line, only the top line. This takes time again because it takes all the 3,800 vectors and tries to make sense of them. So it puts them, it computes similarities between them, and then it tries to reduce it in the end to 2 dimensions. If we see something like this, we're fine. And this, so we have to define a step here, and this is a fitting step, it's called, or a training step. So we showed it all the data we have, and now we want to actually get the embedded. So we want to ask it, okay, give us, if you have to decide in 2D where this thing belongs, give us the 2D coordinates. And then we get a vector that is, here's the same size, right? So you see it's, you get 3,802, which is number of sector, but we only have 2 features in there, or 2 numbers in there. Maybe just for making things a bit clear, what's happening here is embedding UMAP. So instead of this weird shaped 500 vector before, if I now look at the first part, this is what we get. So it now says, the UMAP says now the first spectrum should, if I have to really compress it to 2 dimensions, it's 6.4 and 11.3, right? So that's the position if you make now a plot. This is where the first spectrum will be altogether as well. And this happens for every spectrum. So this we have for every spectrum now. Since we usually don't want to look at numbers, the best way is to do a plot. And this is what we can do by just executing the next cells. What we do is, so far we have no labels in here. The only thing that I can use as a label, or that makes sense for me, is the precursor and that. That's the only information that's useful in our metadata so far, because we haven't added any annotations. I added, so you can skip this part, just believing that it's putting this into a table. And the nice thing about these kind of notebooks is that you can plot things nicely. So this is using a JavaScript related library that works in Python, and it allows you to do interactive plots. So once the complicated part is the computation, the simple part in Python is usually the simple plots. It will look different in workplace maybe because the UMAP is not always doing the same thing, right? So it can be flipped, it can look very different. But this is the pattern that we get. I'll try to make it a bit smaller so you see on the screen. So this is what we get. And the question now is, what do we see actually? We see a number of dots. If we are lucky, this collection of dots has a meaning. Not a perfect meaning, but it has some meaning. And so the idea behind this is kind of that we hope that the embeddings, so the vectors that we get from our deep learning models, are meaningful, that they encode some of the chemistry that's in there. And what UMAP then hopefully does, the second hope, is that it will put points together that belong together. So you can imagine, ideally, if everything works out perfectly, which it never does, but this is something, it's one step towards a chemical map, right? So it's a map of your chemical space of your sample. And we can hover over and we see that, okay, these are the scan numbers, right? So you could also zoom in, and then we see that, okay, there are certain areas which apparently look very different from others. And then you see, so this is now only with the mask. This is not so spectacular, right? So we don't have enough information in this plot yet. Ideally, you would like to color these dots not by the math itself, but maybe more by things like annotations or predicted annotations. So you could import data from, for example, what we see yesterday with Cirrus. You could import the Cirrus data set or the output data, the files, the TSV files, and you could import them and say, okay, take the suggested compound superclass and use it as a color. And if you have something that doesn't work at all, you will see a colorful mix of dots without any pattern. And if it worked, then you will see, hopefully, that there are islands of certain compounds which are clustered together. And then you can say, okay, maybe there's a group of whatever lipids that's in here. And then you can go into the scan numbers and look it up. This is a way, it's probably not the best way to identify individual components, but it can be an interesting way to see, okay, what is the mixture composed of? Because you might see things that you will not immediately see in a network plot. For example, that there are some weird groups that maybe are very different apparently from the rest of the compounds. And there can be that it's, I have no idea, I have to do amateur speculation here now because I'm not, okay. But then you can say maybe this is like traces that don't belong there, or maybe this is a group of things that were added, or maybe this is some other fold, or it's something I'm looking for. And so that's exactly what I hope eventually you could get out of these plots. I think now we're going to do time presentation. So this is how you do this. We can load it. We could load now the Cirrus file. But I'd like to show you one final piece, or just to also show you a bit about this. That we also have a tool which is built on top of MatchMS, which could also help you with annotating these dots a bit better. And I think it's good if we switch to the presentation from Justin, and then we can, or I can also open it. And then I will come back to this notebook, so you can leave it open. I will go back to this notebook and show you how we import. So the final piece of thing we're going to do with this. How we import data into these notebooks and how we then use it to color these dots.
So, well, you are.
I'm just opening the presentation here.
Oh, yeah.
Yeah, of course. Yes, so we will see a bit like what other tool we have that is going to this direction a bit. And I will briefly show you a bit of at least one example of how you could add more information to these cells. So that if you have a name, for example, that's the idea. I mean, this is with the information we have now, we don't have a name. We already have unknown spectra. The only information we have is things like the percent. But of course, if we use MS2Query, which we're going to see here, or Sirius or other tools that add a bit of extra information, we could load it into this as well, so that we can have like a name or a compound class or a smile or something like this on the MS. Yes, we're going to. Briefly, I'll be showing this. It will be in a solution notebook, so you can have to do it. But I will show one example of it. Oh. All right.
So basically, what we also would be interested in is to know whether this blurb of points that many of you have produced, I saw, actually means anything. In other words, can the computer learn chemistry from the spectra? So in my group, we're working on various aspects of computational metabolomics. So going from the spectral data, from a researcher and the spectral data, we work on the organization of the data, and you just saw an example of that, how we can organize a lot of spectra into a kind of a map, so we can try to find out who is related to who. Then we also do work on prioritization of features and samples. That's not really covered in this summer school, but you can find examples through our website or through the QR code. And of course, annotation. And that's the bit that Florian already introduced, like how can we give meaning to the spectra? And one of the tools that we developed is MS2Query, together with Florian and the PhD student, Nick de Jonge, who spearheaded the project. And then hopefully that will lead to insights. So again, with a big thanks to the group, and in particular Nick de Jonge. He's the tall guy in the middle, not to miss. And I hope you will see him later at some point during a summer school or conference. So, and just to be sure that we understand what we mean with kind of identifying and annotation. So the way I see it is that we have seen already examples of library matching, and there we use a database, for example, GPS, to do an exact match. That means that we have a few comparisons to make because we can reduce the search space based on your parent mass. And the question is then, which molecules are in my sample? However, we already have seen that it doesn't work for a lot of samples, that some samples contain only a very few known molecules. So you also would like to see if something is in your data that's related to what we know. And that's what we typically call analog search. So loose match, so you have to do a lot of computations and comparisons. And that is also quite a heavy burden on traditional tools like cosine score, although also improvements there are being made, as Ming showed yesterday in his keynote with Blink. So here we typically ask the question, how do the molecules in your sample relate to those in the library? And yeah, we're looking at the accuracy and speed to see how well all these tools perform. And it's also good to know is why is this actually, or why can it work? And that if we consider the spectra as a kind of a language, right? If we consider the mass spectra as the language of chemistry, then we can also consider each spectrum as a text, as a sentence. And if you're not from Italy, I hope you agree that these two sentence snippets roughly mean the same thing. We can actually draw the lines between the words, yeah, likes and love and cookie and cake, cappuccino and coffee, and we can indicate how alike they are. And typically, our text mining algorithms are invented to do this for you, so you don't have to do it yourself. And the same idea is that Florian and with Florian and others, we coined on the metabolomics data, where each fragment becomes a word and each spectrum becomes a sentence. And basically, you want them to learn how fragments in the data are related. So we then can compare a lot of spectra in a short amount of time, as we just did with Florian showed you like live. And actually, this is part of a whole Python-based metabolomics ecosystem for annotation. So it all started with MS2DeepScore, which I will cover later today, and the Molten Enhancer to combine also that with molecular networking that you have seen already this week. And then we recognize the need for some more kind of standardization and really metabolomics data handling using Python. So then MS was born in a project together with the Netherlands eScience Center. And that was then the basis for tools like SpectroVac, not covered this workshop, MS2DeepScore, just covered by Florian, and all this machine learning approaches kept together in MS2Query. So this is Nick, has been recently published. So if you are interested, please find the publication. Basically combining a lot of machine learning approaches, and it's essentially benchmarked on open data. So if you come up with a new idea, you can directly compare it to what we have seen. It's using the GMPS libraries, a little bit clean, but also that we shared. And basically, the idea is that instead of only using the small part of matches you typically find in the library, we open up more of that information by also looking for analogs, and we're using the machine learning based algorithms to since it's much faster than the traditional approaches, and also gives a complementary view. And an analog can be a molecule that is structurally quite similar, but is different on a few places. Yeah? So we also have seen that the cosine score used in the molecular networking in GMPS is the modified cosine score. That means that if there's only one modification, it can typically still find a good score. But as soon as you get two or more modifications, this modified cosine score also gets into trouble. And that's why these alternative methods can become complementary and find more or alternative analogs. So I brought like a use case again on pseudo-force. I heard them before this week, so that fits quite well in the team. And it was done together with Effie, who used to work here at the DTU, and also on a lot of metabolite annotation related projects. And basically, she got the task to annotate as much as possible in this bacterial extracts. They're really fancy bacteria. I'm not going into detail about them, but they contain a lot of different compound classes, including these iron-catching molecules, which are really important for their survival. And then she used her own workflow called the UMeta flow. If you have a lot of data, then it's really something to consider to use based on OpenMS and PyOpenMS. But the most important thing to remember, the output is again a feature table like we've seen for MS2Query, and a lot of annotations. And now the idea was, can we use the various annotation tools and see how they do for this particular compound class? Now, and then we use the cosine score, we use the hyper score, which is something that is related to OpenMS, and it should work good for peptidic related molecules. We of course use the modified cosine score, and also we used MS2Query. And for this particular compound class, it was nice to see how we could actually start to annotate many more of the pseudo-4 related molecules than with the other tools. I want to warn you, this is of course like a biased view, and but we already have seen how this pseudo-4s have specific patterns that also MS2DeepScore could pick on, as Scott earlier showed. So it's not completely unsurprising that this kind of machine learning tools also can do it. And I checked, and the masses of the pseudo-4s were within the realm of what we could expect. Of course, we also did for the paper an extensive benchmarking using all the DMPS molecules. And so the way we did it is that we took first structure, and then we took out all those spectra, so they cannot find themselves. And which analogs, the question was which analogs would they find? And then we used again the Stanley motor score that Florian already mentioned. And then we checked what that score was. And let's assume for now the higher the better, 1 is equal. Then that means that if we do a random sort in this GPS library, we get roughly 0.2. If we look for the optimal analog, it is 0.9-ish, and then getting closer to 1 if we increase the threshold. In other words, the further right here, we increase the threshold, so we get more and more reliable matches, and you can see that coming back in the scores. But what is for MS2Query was good to see is that across the whole ballpark, it kind of outperformed the traditional scores by returning like structurally more similar analogs. But of course, we would recommend to use it mainly in this realm, this place here, because here is really kind of meaning something. Over here, it simply means that, yeah, the structural similarity is low. Yeah. But I also need to warn you is that even using these libraries introduces bias. So the MS2DeepScore needs known knowledge. It uses structure spectral pairs to train. So we used the GPS library and we did some analysis. And you can see that the library is not uniformly distributed over all the compound class. So we need to take that into account that there is bias in the library. And if we compare the contents of the library with a bacterial extract, we can see that the mass distribution alone is already completely different. So in other words, yeah, also these models are biased, and you will have to validate the results. That's basically what I'm trying to say. And if you want to know more about the substructure annotation, the large scale analysis, there's a review written a couple of years ago that kind of outlays a lot of this background information, because I can imagine it goes quite fast during this week. And in particular, also for this machine learning based approaches that were introduced today, there was a more recent review where we also discuss a lot of them and how they complement each other and how they build on top of each other. And finally, I also would like to share with you that we not only use these embeddings like we just did now, like in the notebook and produce the UMAP plots for initial screening. I also use them during the teaching with the students. So here you see not a 2D representation, but a 3D representation. And it was created by the Wonder Lab in Wageningen. And basically the students need to answer the question, can the computer learn chemistry from the mass spectra? Basically what I just asked you at the start, like, how can we assess that? Well, it's by mapping compound classes on the spectra. In this case, this is from a library, right? So we know the molecules, the GPS library. So we can map their classifier classes on top and color them accordingly. And basically what the students hopefully see in the hour that we do this module is that a lot of the same colors are clustered. And that is a sign that at least the computer finds some relevant patterns to combine structures of the same chemistry, which is on itself, I already think, quite a remarkable feat. And I hope that, yeah, together with Florian and others, we can continue on this to build even better tools. So with that, I want to give the word back to Florian to kind of show you how we can now use the results from MS2Query to map back on the spectra from the experimental data and see what we can learn.
I think I can start right away from this point as well. So this brings me to these dots, right? So here we don't have these colors yet. That's where we stop with the notebook. And what just to show you kind of that we built something on top of. Actually, it's using MS2DeepScore internally. This is MS2Query. But it does a couple of things for you as well. So it's optimized for speed, and it also does something that we didn't do here yet, and namely that is we know that our predictions are not perfect for many reasons. One of the reasons is a bias in the data. So what we do in MS2Query, or one of the things we do is we don't only take one prediction, but we take multiple predictions. And we try to combine them. And then there is a final reinforced model that kind of tries to make something like this. So MS2Query is more reliable than MS2DeepScore alone. And MS2Query, sorry, if you want to run it, it's always difficult to say very simple because this means different things to different people. Well, let's say if you, I'll just show you one thing, how this works. So if you would like to run it on your own, which we're not going to do here, you can say like, okay, I look for MS2Query. And it is on GitHub, as all our projects actually. And so what I just want to point to is it has the key information provided in the README. And essentially, I will not do this now, but if you just want to run MS2Query, MS2Query it has its own library format, so it has a library for GMPS, and we are developing further ones in the near future. But there is one that you can download from Zenodo, and this library contains the GMPS data in some transformed way, but it contains also all the models that you need to make predictions. And essentially, if you want to run it, you can find all the information in the README. Essentially, what you have to do is you have to download the model from Zenodo, put it into a folder. That's not for here because this is a bit bigger and it takes some time. But then you can run, you can have a folder on your computer where you have the library. And download it. In the end, if you want to run it, it's very simple. You have one command like this. So you say, okay, this is a folder with my spectrum data. It could be MGF files, could be MZMX, MZML files. It doesn't matter as long as it's supported by MatchMS. And you have a folder where all your library information is. If you do this, it will start running scripts to go through all the spectra and compare them to the entire GPS library. In this, so we try to optimize in speed, and there's still some optimization that we can do in foreign versions, but it's just to give you an impression. If you run this data set that we got here, there's about 6,000 spectra. On a regular notebook, it will take about 1 or 2 hours. So it's not something we're live coding, but you could easily run it and say, give me the results, give me for everyone the closest analog in GMPS according to our scores. And then you will get back a table, a CSV file with all the information. For here in the workshop, we have provided these files. So you also find in the Google shared drive folder, you also find files for the group 1 and group 2 data sets. So this is if we run the data that we get straight out of MZMine, the MGS files, we run it with MS2Query. Then we get for every spectrum, we get the best hit according to MS2Query in the GMBS library. And this doesn't mean that it's a good hit, right? Because it means it can be that you have compounds in your MGF file or spectra that are very, very different from what you have in GPS. And then MS2Query will still give you a prediction, but it will not be great. But this is something that you have to run outside of a notebook. You can run it in a notebook, but usually that's something you run overnight or you run extra, and then as similar to Sirius, this automatically exports a CSV file, and this is then what you can use for your notebook, for example. These notebooks are here. We have them computed already. So this is the one I'm going to use here because this is for the example data with the path of results and to query in this shared drive folder. Actually, what I do here is I use standard Python libraries to just import a CSV file. Let's see if it works. It seems to work. So I make it a bit smaller. So I'm not just showing the first 2 rows of it. So this is the data. In the end, you get data for all 3,800. Or the other data sets, we did the full scan, so it's for all the 6,000 spectra, let's say. And then what do you find in this data set? So you find that this is the prediction score. So this is the highest predicted Tanimoto score with respect to all spectra in GPS. You can see already in this first case, it's very low. It's 0.4. Right? So I would say that this is not a very trustworthy result. So I would not go for this prediction. But what you can find in there is kind of other things. So you see like a precursor mass difference, and that's the next big thing that, okay, this is not good, right? So you find this is the original compound, 150, and this is the best match according to this, which is like 4 times as high. So this is something that you would later discard typically in your pipeline. But this is how it works. It predicts, okay, this is the information, the UTP, the compound name, and the smiles from the closest found neighbor in GPS. And for this case, it didn't work well. And for others, it also doesn't work well. But you will see that for many, you get hits with a high score. But we don't want to scroll through a table of 3,800 rows. At least I don't. I hope you get through this too much. So we can plot them. And how do you plot them? And that's exactly where these things that we did so far come together. So I can do, okay, I can simple plot is fine. So I can do like some histograms. So this is what I'm doing here is I take all the model predictions and I do a histogram. So this is a distribution, and this just shows you, okay, how among all these 3,800 compounds, what were the findings? And then we see that we find some distributions, and generally that's up to you. There's no fixed experience yet here, but of course this means for all these things left from here, it found the analog with a predicted Tanimoto score, not a real one, a predicted one again, that is below 0.6 or 0.6 or 0.65. So these things are a bit, I don't know, I wouldn't use them to plot them in a serious plot in the end. But you will see that there's also a big group, actually not under the middle group here, with several hundred in total. I think it's like 1,000 spectra, where MS2Query found, apparently it says that at least, it found matches in the GMBS library with a Tanimoto score of 0.7 or higher. Again, this is not the true Tanimoto score because we cannot know the true Tanimoto score, right? So we just have spectrums without any annotation to it. And the network says it believes to some extent that this has a Tanimoto score of 0.8 with one compound in GPS at least. This data we can now use. What we can do is we can use it in the UMAP mapping. And this code I'm just providing, so I would not go through the details. Actually, what we do is we just assemble the data in a way that it's acceptable for the plotting library. And then you can say, okay, what information from these predictions we're interested in. We could say NPC pathway, maybe doesn't make sense here, but we can like superclass and feature ID, of course, is important for us later on to dig deeper. You can add other things if you like later on. But this is just, so now we add the data, the metadata from the predicted data from MS2Query, and we combine it with, this is the important part, we combine it with the UMAP positions. And then we can do the plot that we did before again. But now we can color it, and we can color it by everything that we like. For example, and that's really good this time, is superclass. So we say the color is superclass, and then we say, this is the question that was before. We can also specify if we hover the data. So this is if you got this mouse hover thing, right? So if you can, in this library, you can say, okay, what do you want to show? Actually, I don't want to show X and Y because I can see X and Y from the plot. I want to see the feature number, I want to see the potential analog, and I want to see the Tanimoto score prediction. You could add anything on top of that, if you like. So this is coming back to the question that you can add compound's name, or if you have any information on this, you can add this. Let's see how this works. We should get a similar problem before, but now we have more information in it, right? So now we see that this is not, of course we do, of course, anybody that has done these dimensionality detections, we usually never get these textbook examples of complete separation of colors, but we see that it's not a random collection of colors here. It's clear, you can clearly see that there are very clear patterns. These are the classes, the separate classes that we have, and you can find them back in the plot. And you can see that there are some groups that tend to be one color, right? So you see that some, here's a bluish area, is separately organic acids derivatives, if you believe MS2Query, and you can see other groups. So this is lipids and lipid-like molecules. And if you go on any of these, for example, this one will be amazing. You would see that this one is one that you shouldn't trust too much. You see the MS2DeepScore, the Tanimoto prediction is 04. That's probably not something very reliable, but who knows, maybe it's still got the class right. But then you can go through and you find some with much higher one. Of course, it's a bit tedious to go through all these points and look for the ones with high score. That's what the last piece of code for today is for. And it's really the last thing we're going to execute here is, I have to add this here as well, the color I want to use. So again, superclass. That's another thing I have to change. What we do here is we do a Python for masking. So we select, we do a filter. Let's say we select Tanimoto scores above a certain threshold and a mass difference below a certain threshold. You can add these. I mean, you can add whatever you like. If you say, okay, 100 is acceptable for me, or 10, or 1, it doesn't matter. You can add what you like, and then you will see only the points that fulfill this criteria. Right? This is much fewer points. We can also say, okay, maybe we are too skeptical. Let's say we go to 07, and we'll see, of course, more points. And so this is the same plot as before, but now only with the points that we have a match, or not a match, sorry, an analog found in the GMPS with an MS2Query score above 0.7. And then you could go into these and look them up. You can also zoom into this plot and move around and go closer, pick some areas. So this is a okay-ish interactive plot. So you can, for example, do, I don't know, maybe you would like to look at this reddish group here. Let me go here, and then you see these dots. Then you could see, okay, this is apparently, I don't know if it's true, of course, but this is what we get. We say, so MS2Query says this is benzenoids. This is not the compound, of course, so don't confuse this. This is the closest analog that we found in GPS. So the closest match in GPS is this compound, that I have no idea of what it is, with this predicted Tanimoto score. So in this Tanimoto score tells you at least, it's not super certain that it could be quite a bit away from this, but chances are at least decently high that it has some relationship with this compound. And it makes sense to look into this. Yes. No, there's absolutely no identification. So we cannot, with this method, we cannot identify compounds for sure. So this is not possible here. So really, the only thing we can do here is, I mean, we could, for example, you could add certain information. You could add, for example, it would be interesting to maybe contrast it with the series predictions. So you could add maybe the series compound prediction as well and see, okay, if this is a related compound, maybe that I would, in my understanding, I would say that if those point to a similar compound, then logic has it that it's more likely that it's something like this. But it's not, you'll never get any identification from this. I mean, unless you see that really the math is exactly the same and the score is super high, then you could look at this in a spectrum. If the codon score is then also close to 1, then you might have an identification. Yeah. Oh, you mean that if you know, if you have extra information about this stuff already, I mean, you know already what it is, or Hi. Yeah, you could easily add it. So, I mean, or if you know your way around these Python methods, for example, we use this table here. And this is now just what we got for an MS2Query, but you could easily add a column and say matches you found, exact matches, or something like this. And then for many of them, I guess you would just have no result, right? So there would be none or empty or something. But for some, you might have the result. And then you could add it to the plot as well. So that would be a contrast, right? So if I understand you correctly, it would be reassuring to see like, okay, of one of these dots or two, I have a match, and this is very close to the prediction, so then I can trust it a bit more. Yeah, that is possible. Right. Yeah, that's a good one. You know, I think that if you have any of these information, by sure me, because what we do here is kind of walking blindfolded a bit, right? So we have no clue if these predictions are right. So this is really only to get a first impression of, okay, somehow there seems to be go back to reset the axis here. So there seems to be certain patterns. We seem to have many hands for certain compounds, but yes, before you call it anything close to an annotation, you have to do a lot of first steps. Is there any question on? So I shared the notebooks are all in the solution part, so you could hopefully also rerun them and modify them later on if you like. There's just this last slide here. If you have any questions, not only on the code, on the code of today, but also in general about Python tools, about MS, MS2DeepScore, MS2Query, please reach out to people like me, Justin, because we're constantly developing new features and new methods. And what I said several times, I'm not a chemist, I'm not the expert on the domain side. I'm trying to adapt machine learning and deep learning and data science methods and the Python software development for this kind of community. But I always rely on good collaborations, and so we're always interested in hearing from you people what you actually really care about, what kind of things you need or are missing. And it's not that I mean, given the small team we have, it's pretty pointless to promise you that you can submit us a wish list and we will build this. But it's still good to see like what kind of things are you looking after, and if you are even better, if you are interested in maybe getting your hands a bit dirty and trying to code yourself, even better, because don't be afraid that you are not good enough in coding or something yet. Don't be afraid of this. Really reach out and try to, I don't know, ask us for looking at your code or try to even maybe contribute to our libraries, because this is surprisingly easy sometimes and it can be quite fun. And I had in the past a lot of good learning experience myself to contribute to a library. I really pushed or helped me learn programming a lot, or was a lot of fun I had there. So reach out to us if you have any questions, or if you have things that you cannot done yet with the tools, or you don't know how to do, and then we try our best to help you. Thank you.